We present a scalable approach to sign language production using a co-articulated gloss dictionary to enable fluid and natural sign synthesis. Much of the world's essential information, like government services, welfare schemes, legal rights, apparently available to hearing individuals through spoken or written language. But for the deaf community, this access is not guaranteed. Our solution is to bridge this accessibility gap through automated sign language generation. To demonstrate the effectiveness of our pipeline, we curate Sanketvani 1K, a domain-specific sign sentence dataset with the help of a deaf and an interpreter. This ensures that the generated signs are natural and co-articulated. With the interpreter's help, we identify glosses, mark sentence boundaries, and add tags like MTH for mouthing to capture additional nuances, like facial expressions or spoken influences present in the gloss clips. We create a vector database of gloss-level embeddings using BERT, capturing both lexical and contextual meaning. After constructing the vector database, we move to the inference block. To convert a text sentence into a gloss sequence, we use our text-to-gloss translator, which is powered by an LLM. The model is prompted with ISL-specific rules to ensure accurate translation. For each gloss, we compute its contextual embedding and perform a nearest neighbor search to retrieve relevant motion units, ensuring contextually correct meaning. An isolated dataset alone cannot support this. The final step is to combine the glosses to form a sentence. Direct stitching causes abrupt transitions, so we use an interpolation method. While traditional methods often result in unclear transitions, FramePack produces smooth and coherent interpolations, ensuring greater fluidity and clarity. Comparison of interpolation outputs from 4 methods. A similar grid is presented to deaf participants for qualitative feedback. As visible in the grid, FramePack interpolation better preserves hand shapes and motion continuity, resulting in smoother and more coherent transitions. To examine error propagation, we replace boundaries after each gloss with 8 interpolated frames from each method. This setup highlights how interpolation quality at each boundary affects the fluency of the entire sentence. We compare our pipeline with spoken to sign and Unanimate DIT. Our method produces natural signing and is accurate. Spoken to sign appears less natural, and Unanimate DIT fails to follow the motion accurately. Here we compare the final output of our pipeline with a directly stitched baseline. Our approach generates smoother transitions and more natural signing, while direct stitching often leads to abrupt motion changes. Thank you for your attention.